let's see. So last time we looked at the photon and this is the case for electromagnetic waves. Okay, so this photon is the quantum mechanical version of the electromagnetic waves, and we have these waves, so we could write it as a sine or cosine or exponential, but we'll try to stick to the exponential notation for most of the time. So we have something which looks like e to the I, okay, k x minus omega t. Okay, so this is a periodic function, okay, sines and cosines, and the periodicity is hidden in these variables. So k is 2 pi over the periodicity in space, and omega is 2 pi divided by the period, the time period, okay, with respect to the time variable. And then we said we can write this as e to the I, okay, factor out a k, x minus omega over k t, and this has then the form of an x minus a constant times t, so this omega over k must be the speed of the wave moving in the plus x direction. Okay, so k times c is equal to omega. Multiplying through by h bar, we get h bar k times c is equal to h bar omega. And h bar omega, remember, is the energy of the photon, okay, that we have found out from the photoelectric effect or the black body radiation experiments. And h bar times k then has to be momentum, because p times c is equal to energy for a massless object. Okay, so putting all of this stuff in, you see omega is just e over h bar, and p is, or k is equal to p over h bar. So this wave I can write as e to the I, okay, or yeah, e to the I, p over h bar times x minus energy of the photon divided by h bar times t. Okay, so the wave corresponding to the electromagnetic wave, okay, has this property. Now it turns out that for the electron, we can relate the quantum mechanical wave. This is electromagnetic waves. The wave for the electron is sometimes called matter wave, which I don't think is a good name, but so I'm not going to write it on the board. But in any case, the wave for the electron also behaves in the same way. It goes like e to the I, p over h bar x minus e over h bar t. Okay, so obviously where did this come from? We are trying to walk in the footsteps of Schrödinger and Heisenberg and try to motivate how you would write down a differential equation, the Schrödinger equation, based on something like this. Now, the electron here is a non-relativistic electron. So the relationship between, okay, so for the photon, remember it was P times C was equal to E. In the case of a non-relativistic electron, we have energy equals kinetic energy, let me call it E sub k, because we can have a potential also, p squared over 2m. All right, so we have this wave. It's customary to represent it by the letter psi. So it goes like e to the I, p over h bar times x minus p squared over 2m h bar times t. So if I want to get something like this, okay, so this is the case of a non-relativistic free electron, which means that we do not have a potential. Normally the energy of the electron would be this kinetic energy p squared over 2m, plus we would have some potential in which the electron is in, the potential energy. So this corresponds to, at this stage, the free electron again. Okay, so now let's try to just find a differential equation. So this psi is in general a function of x and t. And how could I construct an equation, okay, a differential equation for psi, which involves these variables x and t. So I want to differentiate with respect to x and t in order to get a differential equation whose solution is going to be this thing, okay? So we are sort of working in reverse. Normally you have an equation, a differential equation, and you try to solve it, okay, to find the function. Here we are trying to motivate the differential equation. All right, so let's first try differentiating with respect to time. So del psi, del t is going to be, when I differentiate this with respect to time, it's going to bring down an minus I p squared over 2m h bar times the psi, again, psi itself, right? Because it's the exponential function. All right. So let me just multiply both sides by I h bar. I get del psi del t is equal to, okay, I times minus I is plus 1, multiplied by h bar is p squared over 2m, okay, times psi. So now I want to bring down, okay, so I want to now use the x derivative to relate this term to some x derivative of this object. Now you see, if I differentiate with respect to x, each differentiation is going to bring down an IP over h bar, right? So if I differentiate with respect to x twice, it's going to bring down p squared over h bar squared, but with a minus sign, right? So let me just do that. So what is del squared psi del x squared? Well, it's going to bring down a p squared, a minus sign, and 1 over h bar squared times psi. So I'm almost there, right? So I can say that this is equal to, because I really want to eliminate p, okay? So this is going to be minus h bar squared over 2m times del squared del x squared psi. Okay? So now I have an equation here. Let me just write it down. I h bar del psi del t, okay, for which this is a solution. Okay? Now, remember where this term comes from? This term comes from this p squared over 2m, which is the kinetic energy. So if I now want to release the restriction that this is going to be a free electron, so let me say in general, which means for cases when V is not equal to 0, well, I'm going to get a potential energy term here. So it's going to be I h bar del psi del t is equal to minus h bar squared over 2m, okay, del squared del x squared, okay, plus this v of x operating on psi. Okay. So we end up with this equation. Actually, this equation is the starting point of quantum theory. Okay? So this is the Schrödinger equation. We'll see that we can also generate a version of this equation for some sort of time-independent solutions. Okay, so this is actually called the time-dependent Schrödinger equation, and we'll just abbreviate it as TDSE. Okay, so this is actually our starting point, and in fact, you'll see this written on the first page of first chapter in Griffiths. That's where we start from. Okay, so this is what I went through some analysis here, which was, I hope, some motivation for writing this out of the blue. Okay, so we have this equation. What is the evidence for this wave nature of electrons? Well, you can construct various types of experiments. There is I'll not go into a great detail of those things, but there is this, for example, this Davison-Germer experiment, in which we take a crystal. Okay, so this crystal has atomic planes, not necessarily only those, okay, which are parallel to this cut, but you can sort of see that there will be other planes like this also. In any case, you have this crystal, and what you do is you take some electron gun and shoot electrons with a certain specific energy onto this crystal, which means it's going to have a certain momentum, which means that it's going to correspond to a wavelength, right? So P is, again, h bar times k. Okay, just like in the case of photon, that doesn't change. And this k is 2 pi over lambda. Okay, and that corresponds to some wavelength. And what happens is, just like light would scatter from two different planes, okay, you have this scattering from this plane and that plane. So the electron is scattered from this plane of atoms and that plane of atoms. And if the angle is right, you are going to get some constructive interference. Okay, constructive interference, but if the angle is a little off, then you are going to get perhaps destructive interference. Okay, and that means you are going to, if you put an electron detector here of some sort, you are going to get lots of clicks here as the electron is coming in, and very little over there. So you get this wave nature of the scattering from these two planes from these experiments. So if you look at, let me see, for a lambda of 10 nanometers, you have something like, okay, this corresponds to, I think, I don't want to give you a wrong number, but let me just see. I think it's 1.5 electron volts or something. So if you want to probe something of the order of angstroms here, this doesn't go proportionally, of course, because energy and momentum are not linearly dependent. You need to shoot electrons with energies of the order of several hundred electron volts. So this is still low energy in this game, okay? Hundreds of volts is low amount of energy. So we call this low energy electron diffraction. And it's a very important tool. It's abbreviated as LEED, okay, LEED. So very simple equipment. Just electron gun shoots at a crystal surface, and it tells you what's on the surface. So we have lots of these devices around in the laboratories, etc. People working with crystals use this equipment to make sure that the surfaces are smooth and such things. Okay. What is obviously interesting is this diffraction. Okay, this interference occurs. Okay, it's not an interference of one electron with another. Even if you send these electrons one by one, you get constructive interference in this direction and destructive in some other direction. Okay? That's because the electron, a single electron itself, behaves like a wave. So if you send just one electron, it will most likely be going in that direction. Okay? So we'll look at that more carefully now, but let's then study what we have, the point that we have arrived at this point. Okay, so we have the Schrödinger equation. Okay, which tells us how psi is behaving as a function of position and time. I have written the Schrödinger equation in one dimension, but you can easily imagine what it will turn into, and it's three-dimensional, right? The second derivative there will be replaced with a Laplacian in 3 dimensions. But in any case, this equation tells me how this psi changes. Okay, so I have in 3-dimensional space, I have this complex function. You see, I have eyes all over the place. Psi itself is complex, so just like I discussed with you last time, this psi has a real part and an imaginary part. So okay, so that's perhaps something like this. Okay, I'm just making this up, obviously. And then what do I do with this object? Okay, so this object is called a wave function and moves in space. Okay, so this is the x, y, and z. So the basic postulates of quantum mechanics is that now if I just look at the magnitude squared of this function, which is going to be some, okay, positive function. Okay. If I make a measurement I'll find the particle to be in some place, okay, some point in the space. And if I just look at what psi of RT magnitude squared is, it is the density probability function for measuring, okay, the electron at x, well, at r. Okay, so there are two components. We have looked at two components of quantum mechanics. One is the wave function and how it develops in time, in space. That is governed by the Schrödinger equation. And then there is this problem of measurement, trying to detect where the electron is. Now, the electron is a particle, so it will be detected only at one point, okay? And the second feature of quantum mechanics is that this psi actually gives you the probability density function for finding the particle to be at a certain particular point, okay? So the second piece is independent of the Schrödinger equation. The Schrödinger equation is a nice linear, relatively easy to solve equation, at least numerically, okay? But this problem of measurement is something different, and I should perhaps say not quite well understood, okay? Some people would claim that there is nothing more to understand. Okay, that's just fact of life. But some people would say that the theory is not complete until we learn how this thing happens. Okay, so there's some problem here. So this measurement leads to what is known as a wave function collapse, because after you make the measurement, after you carry out the measurement, the wave function all of a sudden disappears. In fact, it's now, the wave function becomes, okay, very singular at this point. It's still a little difficult to draw it in 3 dimensions, but now the wave function all collapses onto that point, because now the probability of finding the particle is no longer, okay, corresponds to any uncertainty. Then now I know definitely that it's inside my detector. Okay, so all of a sudden the wave function collapses. So that's a nonlinear process. Yes?
When it collapses, there will be no wave function anymore, right?
No, well, actually wave function becomes something like, if you like, something like a delta function. Then you know where it is, okay? Okay, so we'll discuss that problem a little better. There is some sort of detector here. Okay, some sort of detector which detects the particle. So the particle becomes a part of that detector. Okay, so it's now inside that detector, and after that point on, it obeys a different set of initial conditions. So you still can look at what the electron is doing inside the detector, but it's a different wave function now. Okay, it has collapsed to that. Okay, other questions? Yes.
What is considered to be a measurement?
Okay, that's a good question. Obviously, if this process has questions associated with it, then concepts like what constitutes a measurement, what is a detector, and such things are also things that we need to discuss a little bit. Okay, so let me just move ahead. Okay, so let's make a somewhat simpler arrangement. Okay, a simpler arrangement which demonstrates this wave phenomena, and then we'll look at an even different type of experiment, and I hope you will get even more confused, because this is a point in this course where you should be confused, okay, because it is a confusing sort of thing. Okay, so we are talking about these waves and interference problems. So there's this classical example that's always given, the double slit experiment. Okay, so suppose I have here an electron gun and I shoot electrons. Okay, and electrons have to go through this double slit geometry. And then I want to put detectors here. Okay, so I want to make a very accurate measurement. So I put lots of detectors to find out where the electron hits. Now, all of these experiments could also be done with photons. And in fact, with photons, it's an easier experiment, because photons, you can do it under relatively more ordinary conditions. For electrons, you need a vacuum and such things, but all these experiments are carried out. So these are not hypothetical stuff. These are experiments which have already been carried out in one form or another. Okay? So our theory says this electron is a wave, so it probably starts something like a spherical wave here, but by the time it reaches these slits, it's more or less flat, okay, like a plane wave. So most of the wave just scatters back. What does that mean? Most of the wave scattering back, most likely the electron will be found on this left-hand side, okay? Or if it's absorbed on this material, then it will be found on this material itself. But some of the electrons will pass through, okay, not some of the electrons, some portion of the wave will pass through, okay, through these two slits. And what happens? There will be constructive interference where these two lengths are equal to one another. And there will be destructive interference if the length difference is half a wavelength. Okay? So that means by the time the wave reaches here, it's going to have a strong value at certain places, and at certain places the value is going to be 0. Then again, there will be some constructive interference, but perhaps not that much, because now it has to go at an angle like this, and over here also. So the probability to find the electron, to detect the electron, is going to be large over here, very little over there, again largish there, and so on. So each time I shoot an electron here, it moves, and one of these detectors click. Okay, so this one just says click. Okay, and we have some equipment here which keeps a tally of this. Okay, so it keeps statistics of how many electrons are hitting where. And at the end of the experiment, we find out that the maximum number of hits, so I'll try to make this Okay, so if I call this, I don't know, the z direction, so z direction, so I find out that a lot of electrons hit this point. So if I make a histogram, it becomes very small. So let me be consistent with that picture. It will go down here, another peak there, similar sort of stuff here. It will go to 0. Obviously, you expect it to be symmetric, right? Something like this. So indeed, you get wave interference. So if you start with the fact that the electron is a wave, then of course, this is not surprising. But what is, I think, surprising is this happens even when you send one electron out, okay, just one. It goes and clicks one of these detectors. Then you send, okay, wait perhaps 10 minutes if you have lots of time, send another electron, that flies through, and that makes another click some other place. Okay? So the electrons are not interfering with one another, they are interfering with themselves. Okay? So the electron, although it is detected as a single particle at a certain point, so when we detect the electron, it has to be at a certain point. It seems to be passing through both of these slits. Okay? So the electron, so people who make fun of Copenhagen interpretation say that electron behaves like a wave if you are not looking at it, but it behaves like a particle if you are looking at it. Okay? I mean, it's easy to call names, make names, but then we can make fun of their theories also if you like. So, but that's the idea, that if as long as you do not detect it, the electron just moves like a wave. And if you try to go around this, try to, for example, find out which slit the electron is going through, and if you just, okay, so if you make another experiment and say that, okay, I want to find out which of these slits the electron is going through. So if you put perhaps, I don't know, something like a small door or something to find out what happens when you close it. But if you just close it, then the solution is that of a single slit, which is not interesting because there's no interference. Okay, there's nothing to interfere. So we are going to get large number of clicks here. Okay, so let me draw this in this direction. It's just going to be something like that. Okay, so it's not going to be interesting. So the fact that you are trying to measure or trying to figure out which slit the electron went through interferes with the experiment. Okay, so you have to keep that in mind. All right, so let's move to another experiment. Oh, I should not forget my attendance. So which side is closer? This side is easier. Okay, thank you. Concentrate on the measurement part. So the interference part, the wave part, is something we have to live with. Apparently, electrons do act like waves. We can just experimentally show that they do. Now let's look at the measurement stuff. How does the measurement affect this? You see, I have this wave function which has moved through these two slits, and it's somewhere over here. And the change, the collapse, occurs when I put a detector here, and the detector senses the electron and it clicks. As soon as it clicks, the wave that has appeared here all of a sudden disappears and collapses into the detector. All right, so a different experiment. Again, I have a source of electrons, and I shoot them. Now, this time I'm going to measure some other property of the electron. This is an important property, and we are going to discuss it, okay, at length towards the end of this semester and into the second semester, because it's a nice and measurable quantity. We are going to measure the angular momentum of the electron. Okay, so angular momentum is how fast it is turning, right? And we can, okay, relatively easily find out what its angular momentum is, because since it is a charged object and it's rotating, because of the rotation of the charge, you are going to get a magnetic moment. And because it has a magnetic moment, it can be moved around by a non-uniform field. So if it has an angular momentum in a certain direction, it will be pulled in that direction, etc. So that's called the Stern-Gerlach experiment. And you can measure, for example, since it's a vector, you have to measure it in a certain direction, the component, for example, in the z direction. Okay, so what this equipment does is it applies a non-uniform field in the z direction to the electron. Okay, that's my electron coming in. And amazingly, it turns out that we can measure only two possible values. Okay, there's the value is either plus h bar over 2 or minus h bar over 2. There are no other values. So we say the angular momentum of the electron is quantized. So inside we have this complicated non-uniform field, etc. But what happens is the electron either leaves this way or leaves that way. Okay? So if it leaves this way, it has a wave function which corresponds to a, let me call it psi z plus. It contains a wave function with a plus angular momentum in the z direction. Okay? Or it can have psi z minus. So simple. We have, this is some sort of equipment which separates it, but I have not really detected the electron. It's just still it enters, okay, goes onto these two paths and is flying on its way. So let me block this piece, okay? I don't want the minus z component stuff. Yes?
How can we quantize, how did this component quantize the angular momentum?
We'll have a nice discussion of that when we get to that, okay? So we are, at this point, just trust me for it, okay? But we are going to study angular momentum and how it's quantized in great detail, okay? All right, so just keep in mind that it is just quantized this way, okay? So now I have this flying off like this, and let me now, so I know that it definitely has its angular momentum in the plus z direction. Now if I measure the angular momentum in the z direction again, I'm going to get the same thing. Otherwise the measurement, the concept of measurement doesn't make sense, right? If I measure something to be 5 centimeters, and then I say this is 5 centimeters, but if I measure it again, it's now 7 centimeters, then that means that's not a good measurement, right? Each time I measure it, I get a different value. So here I get plus h bar over 2 for the value of the angular momentum. If I measure it in the z direction, I'm going to get the same thing. But let me measure it in some other direction. Let me measure it in a perpendicular direction, x direction. Okay? So I turn my magnets around, etc. So this thing is coming in, and it separates into two pieces again, and it is either plus h bar over 2 or minus h bar over 2. So again, no matter which direction I choose, I get this possibility of plus, okay, h bar over 2 or minus h bar over 2, as long as it's perpendicular to the z direction. Okay, if it's something close to the z direction, obviously, then things will be different. But if I measure the angular momentum in the z direction, and then I try to measure it in the x direction or the y direction, again, I get 50-50. All right? Now, let's do some interesting stuff. What happens if I now measure, okay, so the psi here is, based on the latest measurement, is x plus. But I'm curious whether this z plus has survived this measurement. So now I take this electron beam. I'm not interested in this one, so I block that away. So again, what is happening? I am sending these electrons one by one. I send one electron, it flies off in this direction. Then if it flies in this minus direction, I just throw it away. And if it is going in that direction, now I am going to measure LZ again. Okay? So what would be your guesses be about what I get here? Hmm? No change, you mean? But what does it mean? Okay, so let's just go all the way back. I'm shooting these electrons. Since z direction is nothing special, I get 50% of the electrons going that way, 50% that way. Okay, there's no reason they should prefer plus z or minus z. Thank you. Okay, space is isotropic. So this is a perpendicular direction. Again, if I do something in the z direction, okay, x direction is symmetrically perpendicular to that, I'm going to get 50% here and 50% there, right? Okay, at least that's what the experiment gives me. Now, tell me the percentages for plus h bar over 2 and minus h bar over 2. Yes? Yes, 50-50. Why? Because this measurement has destroyed the previous measurement. Okay, so we say that these two measurements are not compatible with one another. So I get 50% here and 50% there. Okay, what about if I do the same experiment with these guys? Okay, so I get the minus x stuff, and I again measure LZ. Okay, so again, these things can go both ways. What about the percentages? 50, yes. By now you are getting to these, used to these 50%, right? Everything seems to be 50%. Okay, so very good. Things seem to be going okay. So if I measure these electrons, I get 50-50. If I measure these electrons, I get 50-50. Yes?
What happens to the conservation laws in these kind of mechanisms? Because, for example, how do they define conservation of momentum?
Okay, when you are making a measurement like this, okay, when you are doing something to the electron, here you have a certain magnetic field, etc., those things do not conserve the angular momentum, because a magnetic field will apply a torque to the system, to the magnetic moment, and because you have a torque on the magnetic moment, it will precess, so it's going to change its direction. So we cannot claim that there is any conservation of angular momentum here. Okay, now let's modify this experiment just a little bit. Let's say, okay, I'm going to I did these measurements. So let me just take these two beams that I have like this and combine them into a single beam, and let me measure LZ now. Okay, so here it goes in these two directions now. What about the percentages in this case? Any guesses? Well, it looks very reasonable that it would be 50-50, right? But you see, what I have done is I have not really made a measurement here. Okay, so I was looking the other way, and these things separated, but then they combined. So since I have not collapsed the wave function into a detector, okay, the wave function is still robust, okay? So this event here just reconstructs the wave function that I had over here. I have just separated two components, but then I combine them together again. So I'm going to get 100% plus h bar over 2 and 0% minus h bar over 2. Okay, because I have put a detector here which is now measuring stuff. Okay, so the measurement itself is actually modifying the wave function. Okay, so over here, since I have not made a measurement, what happens is that this wave function is split up into two pieces. Now, if we go into a little bit detail of what is going on here, the Schrödinger equation is a linear differential equation. What does that mean? If I have a solution, if I have psi1 is a solution, and if also psi2 is a solution, then, okay, a linear combination of psi1 plus b psi2, by the way, I use capital psi and small psi interchangeably, is also a solution. Yes?
Well, I still couldn't understand that. Why the last part for LZ, we say that we didn't have a measurement. I mean, we converged them, but how can we conclude that we didn't have a measurement?
Okay, so that's what I'm going to get at. Now, you see, what we have when we write this psi z plus, it turns out that this psi z plus is actually maybe written as a linear combination of the type of wave functions that I am going to get over here. Okay, so in fact, there's a factor 1 over square root of 2. I'll discuss what I mean by writing that over here. It's psi x plus plus psi x minus. Okay? So what happens is that this psi x plus plus psi x minus are two possibilities that you can get out of this wave function. Okay, so the total wave function is psi z plus, which is flying over here, but it can be written as a linear combination of what is going to come out over here. So I can either get this one or that one out of that path splitting. Why do I need a 1 over square root of 2? Because the square magnitude of this is going to give me the probabilities, 1/2 for this one and 1/2 for that one, okay? We are going to discuss those technical details later in more detail, but at this stage, just see that this is actually these two wave functions added together. Similarly, this psi x plus is just 1 over square root of 2 psi z plus plus psi z minus, and psi x minus is 1 over root 2 psi z plus minus psi z minus. Okay, so what I have done here is I have just separated this wave function into two of its components, but they are still parts of the Schrödinger equation solution. So the Schrödinger equation is still working on them, except that instead of identifying them as psi z plus, I identify them as these two objects. If I make a measurement here, then it collapses to psi x plus. But otherwise, when I combine them together, I get my psi z plus back. You can even see that if I were to subtract one from the other, I would get a psi z minus. So if I did some sort of perhaps phase shift so that I shifted this psi from plus to minus, I could get the other path also. So this business of measurement is something crucial in obtaining the result, because that's what we are interested in, right? So suppose we made all this equipment, okay? So we are a company which is trying to produce psi z pluses over this, okay, set of experiments. How do I do that? Well, I do that with an experimental setup like this. But what is going to be important is I feed electrons at this end, and I want to get psi z pluses at that end. So that's what I'm going to measure. Obviously, I could get them over here, but suppose I wanted to make the equipment more expensive or something, okay? So in that case, I just look at what is coming out here. I put my detector there, okay? And I just measure the electron coming out here or there. And as soon as you make that measurement, okay, the wave function will collapse. So this measurement stuff is separate from the Schrödinger equation itself. And let's perhaps have our break at this point.